Welcome back, everybody. This is our 12th class in JEE mains previous year questions for chapter current electricity. Till now, we have made 11 videos in this series, and all of those videos are available on our YouTube channel. Name of channel is Point Basics, and there is a dedicated playlist for these type of videos. We have also started similar series for NEET previous years, so you can go to our channel's playlist section and find those videos out. And if you find those videos useful, helpful, then do press the like button, share them, and subscribe to our channel. It helps a lot when you share and subscribe. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Your donations, however small, will be helpful to us in making these videos or bringing these videos on a regular basis. So with this, let's start today's video. And in previous video, we have completed up to question number 100 I also think. So this was the last one which we covered. And today we will start with question number 101. So electric bulb is rated 220 volt at rated to 100 watt at 220 volt. The power consumed by it when operated on 110 volt. So when normally whenever we are given some power of some appliance, then some potential has to be given with it on which that power is calculated. And if that potential is not given, we by default take the whatever potential is mentioned in the question. So in this question specifically mentioned that 100 watt power is at 220 volts. So first of all, what we do, we will find the resistance, and then using that resistance, we will calculate the power at 110 volts. So we know that power is equal to V square by R. So from this formula, R comes out to be V square by P, which will give us 220 into 220 by 100 value of power, and 22 into 22 484 ohms will be the resistance. Now we know the resistance of the instrument or the bulb, and we also know the potential on which it's operating. So we can again use this formula that new power or P dash will be V dash square by R. Here V dash is the newer potential, that is 110 divided by resistance, so 484. And this 484 we can write 22 into 22 to make the calculation easier. 22 into 22. Now we can cut these on 11s. 22 into 5 is 110. So 5 into 5 will be 25 watts. So that's how our final power at 110 volt will be 25 watts. So option C will be the right answer. Moving to next question. A heater coil is cut into two equal parts and the only one part is now used in the heater. The heat generated will now be. Now in this question, we only know that the coil is cut into two parts, but we don't have any idea regarding the potential. That assume this is our first coil, initial coil, and it was connected to a battery source of potential V. Now, when we cut into half, so suppose now it's half, so we assume that battery source stay the same. So its initial resistance was, we can say R, and final resistance is R dash. Now we have solved this type of questions already in the previous chapters of class 12th, that suppose some resistance has resistance R, and if we cut it into half, then its resistance becomes N square times R, where N is the ratio of final length to the initial length. We have solved some question where length of a wire is doubled. We have solved this type of question, that length of a wire is doubled and now find the resistance. So in this scenario, n becomes final length by original length, that is 2, and resistance becomes 2 square times original resistance. In this scenario, the coil is cut into two equal parts. So now new length new length becomes half of the original length, and what we have, n becomes 1 by 2. But in the upper part, in this one here, area does not stay constant. Area is not constant, but here in this scenario, because we only cut it into two parts, area is constant. Or we can simply use the formula for resistance, that R is equal to rho L by A. This is the original resistance. Now our new resistance, rho times new length, that is L by 2. Area stays the same, and it is half rho L by A. So this is the original resistance R. So R dash is equal to R by 2. So now resistance is reduced to R by 2. Assuming potential stays the constant, so power will become V square by R by 2, or we can say P dash it is. So twice of V square by R, and V square R by R is the original power. So twice of the original power. So option B, double, is the right answer. Moving to next question. The resistance of a hot tungsten filament is about 10 times the cold resistance. What will be the resistance of 100 watt and 200 volt lamp when not in use? So as per the first line, resistance of the host or hot filament is 10 times the cold resistance. So suppose resistance of hot filament is RH and resistance of cold filament is RC. So as per statement, RH is equal to 10 times of RC. Hot resistance is 10 times of the cold resistance. Now, what is the resistance of 100 watt 200 volt lamp when not in use? Now, assume bulb is working, or that filament or lamp, you can say lamp is working. It is mentioned that lamp is working. So if lamp is working, what is doing? It's consuming 100 watt of power at 200 volt. So when lamp is working, it is consuming 100 watt of power at 200 volt. So what we can do? We can find resistance while it's working. Now, while it's working, it will be considered as hot, because while it's working, it's generating heat. So filament will be heated, and its resistance, as per the question, will be considered as a hot tungsten filament resistance. So RH will be V square by P. So it will be 200 into 200 divided by power, that is 100, and it comes out to be 400 ohms. So RH is 400 ohm, and using this, RC will become RH by 10, that is 40 ohms. So when not in use, its resistance is 40 ohm, and when it's in use, its resistance becomes 400 ohms. Moving to next question. The thermosists are usually made of metal oxide with high temperature coefficient and resistivity, metals with high temperature coefficient, semiconductor material, metals with low coefficient of resistivity. Now, thermosists as the devices. These are the, we can say, devices, or we can say materials. Material will be the right word. Materials used to sense small changes in temperature. Now, if they have to sense small changes in temperature, means their temperature should change by significant amount. Oh, sorry, not their temperature, their resistance. Their resistance should change with significant amount with change in temperature. If their resistance stay constant with changing temperature, then they cannot work as a sensing instrument or sensing material. So their resistance should be significantly changing with temperature, and it should be linearly changing with temperature. Their curve with temperature, their resistance versus temperature curves line follows a straight line. So if the temperature, if the resistance is changing with temperature, means their coefficient of resistivity or their alpha is quite high. Their thermal coefficient or thermal alpha, their temperature coefficient should be very high, and hence the option B, I think, metals with high temperature coefficient of resistivity. Actually, it should be metal oxides. Okay, that's mentioned in the option A. So option A, metal oxide with high temperature coefficient of resistivity, is the right answer. Moving to next one, temperature taken by 836 watt heater to heat 1 liter of time taken by 836 watt heater to heat 1 liter of water from 10 degrees Celsius to 40 degrees Celsius. So we are increasing temperature of water from 10 degrees Celsius to 40 degrees Celsius. So amount of heat will be required to heat this water to bring this change in temperature will be mc delta T, whereas m is the mass of water, c is the specific heat, and delta T is change in temperature. So mass of water, for water 1 liter is equal to 1 kg. So 1 into specific heat of water is 4022 joules per kg, and into change in temperature, that is 40 minus 10, that is 30. So total heat required will be 126,000 joules. So this is the amount of heat required. Now uh, the heater we have, that heater is producing 836 joules per second, that is power, its power, joule per second is watt. So in a 1 second, in 1 second it's producing 836 joules. So how much time it will require to produce 126 into triple 30 joule, assuming no heat loss, assuming no heat loss to surroundings, 836 into some time should be equal to 126,000, and times comes out to be 126,000 divided by 836, and it will be 150.7, or approximately 150 seconds. That is option A as per our solution. Moving to next question. A 220 volt 1000 watt bulb is connected across a 110-volt main supply power consumed will be. So again, in this question, as we done in the previous one, first we will find its resistance, and then using that resistance we will calculate its new power, and it will be mostly 250 volts. As potential is reduced by 2, power will be reduced by twice square of the potential. So we know that power is V square by R. From this, R is equal to V square by P, and initially potential is 220 and power is 1000. So it will be 22 into 22 by 10. Now new power will be new potential by resistance, because resistance will not change. So new potential is 110 into 110, and resistance is 220 into 220 by 10. So this will go on 5, so 250 watts. That is option C. Moving to next one. A wire when connected to 220 volts main supply has a power dissipation P1. Now wire is cut into two equal pieces which are connected in parallel to the same supply. Power dissipation is P2, then ratio of P2 and P1. So suppose this is a wire and it has some resistance R. So its power dissipation will be given by V square by R. So 220 square by R. Now this wire is cut into two equal pieces. So each piece will carry half of the resistance. So suppose this is the first part, resistance R by 2, and this is second part, resistance R by 2, and they are in parallel. So they are in parallel and they are now connected to same supply. As they are in parallel, their combined resistance will be R by 4. And now new power will be, and so we can say this is P1, and now P2 will be again V square by V square by resistance. So V square by resistance is now R by 4. So R to 4. So now if we divide P2 by P1, what we get? 4 times 220 square by R, 220 square by R. 220 get cancelled and we get 4. This question can be easily solved even without using any mentioned value of potential. We can just take potential as V. Oh, moving to next one. If in the circuit power dissipation is 150 watt, then R is. Okay, so we have two resistances here. One is R and another one is 2. Both are in parallel, and as a whole they are consuming 150 watt. So their parallel combination, we can say their total resistance is RT, and RT will be equal to their parallel combination 1 by R plus 1 by 2, and it will become 1 by RT is equal to 1 by R plus 1 by 2, and from this RT will be 2R by R plus 2. Now as we know the potential, so power consumed will be V square by R. Value of power is given 150. Value of potential we know, that is 15 divided by R. So 2R divided by R plus 2. That's get cancelled at 10. And again this gets cancelled at 3, and this is at 2. So we have 2 here equals to 3 times R by 2, R plus 2 divided by 2R. So 4R is equal to 3R plus 6, and from this R is equal to 6 ohm. That is option B. Moving to next one. Two resistors 400 ohm and 800 ohm are connected in series across a 6-volt battery. The potential difference measured by the voltmeter of 10 kilo ohm across the 400 ohm resistance will be close to. So here we have to apply the concepts of potentiometer and how it actually measures the potential. So for that, let first draw that circuit diagram. Here we have 400 ohm resistance and in series with 600 ohm resistance. They are connected to a 6-volt battery and measured by a voltmeter of 10 kilo ohm. So here we have a voltmeter connected parallel to 400 ohm resistance, and this voltmeter has a resistance of 10,000 ohms. Now in case of a ideal voltmeter, in case of ideal voltmeter, its resistance will be infinite, and we can easily find out potential across 400 ohm resistance. It will be just current times resistance, and current in the circuit will be 6 by these two resistance, both are in parallel or series, so their combined resistance will be 1000, multiply by, this is the current, multiply 400 ohm, so it will be 2.4 volts. But in this scenario right now, this voltmeter is not ideal. So we will just consider it like a normal resistance. So we have to consider it like a normal resistance, and then we will able to find out what value it will show. So we will redraw the diagram. We have a 400 ohm here, 600 ohm here, and in parallel with 400 ohm we have a resistance of 10,000 ohm. So this will be our new diagram. Now this 10,000 and 400 both are in parallel. So what we have to do, we have to find their combined resistance. So their combined resistance will be 1 by 400 plus 1 by 10,000, that is equal to RC, combined resistance. And after solving this, uh, we can uh, we can get an idea, as 10,000 is very large as compared to 400 ohm. So the final resistance of their combination, parallel combination, will be somewhere around 400 ohm, somewhat less than 400 ohm, and actual value comes out to be 384.6 ohm. So now total resistance of the circuit will be RT. Their parallel combination is in series with 600 ohm resistance. So their total resistance of the circuit will be 384.6 plus 600. This will be 984.6 ohm. So this is the new total resistance when voltmeter is not ideal. So now we have the total resistance. We know the potential, that is 6 volts. So current will be potential by resistance. So 6 by 984.6 ampere, this will be the current. And as we have to find out voltage across this 400 ohm, what we will do, we will actually find out the voltage across their parallel combination, and their parallel combination has a resistance of 384.6 ohm. So volt across their parallel combination, that RC, voltage across their parallel combination, RC, will be current times resistance of the parallel combination, 6 by 984.6 multiply 384.6, and this on solving give us 1.95 volt. That is option D. So that's how you do this type of question when where voltmeter is not ideal. What you do, you simply take voltmeter as a normal resistance, and then take their then calculate their parallel combinations final resistance, and assuming that final resistance as voltmeter, you just calculate the potential across it, and in this case we have 1.95 volts. Moving to next one. Which of the following will not be observed when the multimeter operating in resistance measuring mode? Probes connected across the components are just reversed. So here our instrument, or what you can say our multimeter, is working in the resistance mode. So when it is working in the resistance measuring mode, what will it do? It will, we can say, suppose this is our multimeter, and these are its two terminals which we are using to measure the resistance. This is terminal A and this is terminal B. So to measure the resistance, we know V is equal to IR from the Ohm's law, and from this R is equal to V by I. So when you connect some component between A and B, there must be some potential and some current flowing from A to B or B to A, and only using these values V and I, it will calculate some value of resistance, and then it will display on its we can say its scale, on its scale or its digital display, that what is the value of resistance. So this will be the basic working of the multimeter in the resistance mode. Now coming to the point A. Multimeter show equal deflection in both cases before and after reversing the probe if system chosen component is resistance or resistor. So if we choose some resistance and connect A and B point to its terminal, and even if we reverse it, if even if we reverse this resistance like this, even we reverse it, the value on the multimeter scale or display will not change, as resistance, a resistor is not a active component, it is a passive component, and it does not have any positive or negative terminals. So deflection will not change, and option A is right. It is okay, this will happen. Multimeter show no deflection in both cases. It means before and after reversing the probe if chosen component is capacitor. Now chosen component is capacitor, and we know how capacitor works. Suppose we have a capacitor and multimeter works on a DC multimeter works on a DC voltage. We have a DC supply inside it. So when measuring between A and B, it's measuring DC voltage. So when we have a capacitor and we connect terminals A and B to this capacitor, what will happen? Suppose we have connected terminal A here and terminal B here uh, of the multimeter to the capacitor. So initially capacitor is discharged. So what will happen? That capacitor starts charging. And now if capacitor is charging, there will be some potential across it and some current across it. So it will show some resistance. And after some time, capacitor will be fully charged. And when capacitor will be fully charged, it will show there will be maximum potential drop across it, but current will be zero. As capacitor is fully charged, no current will flow across the capacitor. So now we have I zero and potential is there across it. So resistance, which earlier one has a finite value, suppose 2 ohm, 3 ohm or some value, now it becomes infinite. And we know that for a capacitor, resistance or its capacitive reactance is given by 1 by omega c, where omega is the frequency. For DC supply, frequency is 0, so its capacitive reactance becomes infinite. So a capacitor does not conduct DC. So it will show deflection. Even we reverse it, the principle will stay the same, process will stay the same. So it will show deflection, and its deflection will something like this. Initially, it will go slowly. The scale, we can say, initially it will go slowly and then it will go to the maximum possible value. So as per mentioned that it will show no deflection, this is wrong. So option B is wrong. Coming to the option C, multimeter show a deflection accompanied by splash of light out of connected and no deflection on reversing the probe if chosen component is LED. Now, if chosen component is LED, what will happen? LED will conduct, because LED, what is LED? LED is a PN diode. LED is just a PN diode. So when this diode is forward biased, when this diode is forward biased, and we are connecting A and B to its terminals, assuming A is initially positive and B is negative. So this diode will conduct and this will emit some light. So this diode will be working and there will be some finite value of resistance. So C is right. And multimeter shows no deflection in both cases, in mean before after reversing, if chosen component is metal wire. Now if chosen component is metal wire, what will happen? Metal wire has a approximately 0 ohms resistance, because it is made of metal, and metal is a conductor and conductors have a very small resistance. So metal wire will have very small resistance, which is might not be measurable by this multimeter. So it will show no deflection, and again metal wire is a passive component. It does not have any positive and negative terminals, so reversing it will not make any changes. Hence, there will be no deflection. So option D is also right. So option B will be the final answer, which is the wrong one. Moving to the next one. Here we have a potentiometer wire PQ of 1 meter length is connected to a standard cell E1. Another cell E2 of EMF 1.02 volt is connected with resistance small r and switch S. When switch S is open, the null position is obtained at a distance 49 centimeter from this point. The potential gradient in the potentiometer wire is, so we have to find out potential gradient of the potentiometer wire, or in short, what we have to find out? We have to find out potential drop across PQ wire by its length, that is 1 meter or 100 centimeter, because all the answers are in centimeter. So now let's discuss the cases. Now as per this part of the question, that when switch S is open, the null position is obtained at distance 49 from the Q. So we can say this value of this JQ when S is open for balance condition is 49 centimeter, and value of PJ is 51 centimeter. And at balance position, or we say in balance condition, where we get null point, No current flows in the circuit. No current flows in the circuit. And which circuit I'm talking about? I'm talking about this one. In this circuit, there will be no current. Not in the PQ part. In the PQ part, or we can say, let me circle here. Inside this green circle, there will be some current flowing. But inside this red circle or in this pink circle, there will be no current flowing. Okay. So if there is no current flowing in this pink circuit, so total potential we can say, if we say this is point A and this is point B, potential between A and B will be equal to E2. As no current is flowing, there is no current or no potential drop across this resistance R. So potential between A and B is equal to E2, and that is equal to 1.02 volts. Now assuming potential gradient of this PQ wire is we can say X. So let assume X is equal to potential gradient of wire PQ. Now if X is the potential gradient of wire PQ, we can easily find out potential developed across wire, and let's say potential across P and J points, potential developed across P and J points, or we can say VPJ, will be equal to potential gradient X into length of that component, that is 51. So X into 51, and we can see from this diagram P and A are connected, J and B are connected. So as these points are connected, we can say that VPJ should be equal to VAB, and VPJ is equal to 51 into X, and VAB, that is equal to 1.02. So from this X comes out to be 1.02 by 51, and we can write it like 102 into 10 raised power minus 2 by 51, and that will be 2 into 10 raised power minus 2, or 0.02 volt per centimeter. Option A is the right answer. In these type of questions, normally we do all the calculations at the null point, and in the null in this we can say at null point there is no current flowing on the second cell, not in the first cell. There is current flowing from P to Q. Due to that current, there is some potential drop, we can say some potential drop is happening from point P to J, and that potential drop is balancing this cell, and that's why we are getting a potential gradient here. Okay. Now using this value, we can also calculate value of E1, and value of E1 will be equal to potential between P and Q points, and potential between P and Q points is equal to potential gradient into total length, and total length is 100 centimeter. So we can say it is 2 into 10 raised power minus 2 into 100, and that is equal to 2 volts. So E1 is equal to 2 volts, and E2 is already mentioned in the question. So with this, we end this video here. Hopefully whatever we have covered is helpful and useful to you somehow. And again, if you like this video and find it useful, then do press the like button, share it as much as possible, and subscribe to our channel. And also, if you like to donate us and support us financially, you can scan these QR codes in front of your screen and donate us with whatever amount you want. Even a small donation will be highly appreciated. So with this, thanks for watching and we will meet in next video.